All right. So the main reason why I set out to do this is because we were having lots of problems when we were deploying our code to production. As you know, we are an e-commerce company, and for every little error, every little thing can have a substantial impact on economics and financial outcome of the company. So we were finding ourselves just constantly investigating production failures rather than improving our coverage and our tests in general, and we found that we were adding test cases and more test cases, and that wasn't necessarily preventing a lot of the production issues that we're having. So drawing a parallel from the previous talk, if you were here, it's just like, do we even need to create those test cases? There's some truth to that, some truth to the fact that you need to have certain test cases to do some basic function validation, and then you need to use some of the production data, which is why I go to this process. Basically, we established something called the Canary, and it's actually a very common thing in the industry. I've used in many companies I've worked at. But basically, the Canary term comes from the mining, and then the miners would go down to go mining coal, whatever they're mining, and they would bring Canary, a bird, with them. And if the bird starts looking lethargic and stops moving or stops chirping, they know they need to get out of Dodge as soon as possible because there's some gas or something that is basically probably carbon monoxide or something else that is going to be lethal to that. So the poor bird is sacrificed in the process, but it saves the lives of all the miners that are out there. So the parallel to distributed production when you're deploying online systems is that you should basically deploy, instead of going, when you sign off on a new build, instead of deploying that to the entire production system, you deploy it to a very small subset. And then you take some measurements of that data. And then you make a final decision on whether you're going to go to production or not. I had actually had more data to share earlier on, but then, after PR reviews and things internal to the company, they made me change to a much more boring data set. But what we have here is because everything's perfect, right? So we have to show here is basically what I have is two different data sets from two types of servers. So I have here the blue lines counting the amount of 4XX errors. So basically, HP request 400 or a variant of it, and the pinkish one, the 500s. So we're looking at one server which is called a Darwin Canary. Canary meaning like the actual canary taking live production traffic. And the other one, which we weren't so sure about this build, so we actually evolved the process, created something called a dark canary, which is a subset of production that only receives forwarded traffic from production. So in other words, it's not interacting with the customer. The build's not interacting with the customer whatsoever. Yet we can do a perfect A/B comparison because we have the host that's receiving the live production traffic, then we forward that to the other host that is receiving just the forward. So the responses from that host are not going to be sent back to the customer. So we were finding ourselves basically staring at these graphs and trying to make a decision on whether this build was good or not. And then we just basically eyeball things. It's like, it looks about the same. But that one in the left, the Canary, looks a bit higher than the other one. Is just okay? Is there a new set of requests that is now failing, returning more 400s to 500s I can barely even touch? So it's looking out to see you need quantitative methods to try to determine and basically come up with an answer that's more than, hey, it looks good to me. And therefore, that's when we came up with these things. So before I'm going to cover a little bit of theory, I'm just going to brush over it, and then the goal here is not to really teach that, but just kind of to highlight the basic concepts that help you interpret the data that's coming after that. So basically, the first thing that we're trying to do is break out the percentiles. And then, big disclosure here, this is a Gaussian curve based on normally distributed data. And the data that at least we see is hardly ever normal. So basically all the tests that we had to do was they had to be picked and chosen based on the fact that they're testing non-normal data. But this actually helps highlight the concept of you have a group of data. So it's basically, then you have here, in this particular case, you have plus or minus 1 standard deviation. we get about 68.2% of the total data set. And then as you start going forward, you have another 27.2. So basically you already have about 98% of data covered in that space. So it's basically your data is spread all around. And what this means is basically, so this is straight out of Wikipedia. So if I have a data set that is distributed as 3, 6, 7, 8, 9, 10, you just apply the formula. And you get the 25th percentile ends up being the actual third member of the array, which is number 7. And then it just keeps going and going like that. So it's basically, it's how to break out the data in different percentiles so that you can actually see how this data is changing over time. Then things start getting a lot more interesting. All right, so it's basically what we do with the data is start with the basics. So what we did was break a 0th percentile. Why? Because we want to know whether that bottom, whether that basically the floor of the error threshold is going up or down. Right? And then that's very important for us to know that. And then a bunch of them in between, and you will see there that we have 90th, 95th, and 99th percentile. Why? Is because, well, we want something to be, our error rate to go no more than 1%. So therefore, 99th percentile is very important to find out if that's changing or not. And then the mean, which takes the entire data set into consideration, the median as well, but gives us a different view on it, and the standard deviation of this data. So it's basically, these are very basic things that you can use any tool out there to basically break out the data. All right, so when we move to that, I'm going to show you for the graphs that I showed earlier, you will see basically that the Canary Host, the 0th percentile, basically the floor here, is the same. There was no change to the bottom of that data. So basically we know that the new build is not introducing errors to the point that it's always, the floor is always higher than the other one. When you start looking at the 25th percentile, you start seeing the Canary Host is slightly better, 75th, and as you start going up in the percentiles, you start seeing more variation. Just because it's the nature of the data, there are less samples there, so there's a lot more variation at that point. So basically, you start looking at it, and you can see the Canary Host showing slightly better numbers as far as the mean, median, and standard deviation. Okay, so it's a bunch of numbers, yet it's kind of hard to see a little bit. How do I move on to the next step to add more clarity into this? Well, then here's a thought. Ratios. So basically, you divide one by the other, and if they're about the same, they should be around 1. All the ratios should be around 1. If they're less than 1, that basically means that the denominator is higher than the numerator. If they're more than 1, the numerator is higher than the denominator. You guys all know basic math. You can do math and figure out which one's that. So it's basically, as we start seeing this, we're like, oh, look at the 25th percentile. So all of a sudden, you know, my Canary Host is looking a lot better. And you see here that my Canary Host consistently less than 1. So now I can see, well, now I'm starting to build more confidence in this data, showing that the Canary Host is definitely, at least when the ratios, is looking a lot better. And this gives you a lot of clarity already in that data set. So moving on, so another tool that I like to see for those of us that are more visual than numeric, there's a very cool tool out there called box plots. So it's every simple statistics basic package should be able to plot you a box plot of the data. So when I look at that, what is so important about the box plot is that the difference is that you've got to focus on something called IQR, which is the difference between the 25th and the 75th percentile. So it focuses on that core of the data, where the majority of the data is situated at. And basically it gives you a graphical analysis. So it's like, if you see here, it drops down to the distribution. Again, this is for a normally distributed curve, so your data will look different than this. And I'll show you what the data looks like in a few slides here. But you can see basically that it covers the majority of the data, and that's what the goal is. So understand that basically the box plot is going to basically cover the vast majority of the data and give you like a visual interpretation of what the results look like. So when I plot the data from those two hosts, from the Canary and the Dark Canary, I could see that the canary is basically giving me, that the floor is about the same, which is what we found on the previous 2 slides ago that showed that the floor is really not moving. But then what it showed us is that the canary, which is the dark canary in this case, has a lower mean, and that black line in the middle actually shows that. That's what that black line means. The actual mean, the very center of the data is actually lower. So it's having lower error rate than the reference host, which is a good thing. The other thing that I see is that my 75th percentile is lower than the other one, which is another very important thing for me to note, basically. And then this thing right here is what it kind of chops off. It's like the very top, that little bar there at the top is what the statistics package will basically remove some of the data and consider everything after this point as an outlier, something that is more of not important or not meaningful to the data set. So what it considers that at this point, the top error rate for the canary, which is the build-in evaluation, is pretty much much lower than the other one. And what that means is that basically this box plot clearly shows me that my canary data is being is looking very promising right now. All right, so let's look at histograms. So this is a very basic thing. So if you had a tray with multiple slots for you to start stacking up Oreos, that's what a histogram would be. So basically, this is a very simple thing, heights of black cherry trees. So you have a population of black cherry trees, and you start measuring their heights. And then when you see them, hey, I have something that's about between 75 and 80 feet of height, I end up having about 10. I have 10 observations within this population. And then within 7 and 75, I have 8 observations of the population. So basically, it's just really every time that you see an observation of the population, that counter increases. All right, so basically, one more explanation here that makes a better analogy to the data that we're looking at. It just brings it down between the different bins. And again, this is a very normally distributed, which is all the examples you find out there, they like normal data just because it looks pretty and easier to understand. But you see the different bins covering different data points, and then whenever you have one point of your data set that matches that bin, it adds that counter, and it just kind of adds up into that way. All right, so now that we've covered the basics about histograms, let's look at the histogram of the data that we were evaluating earlier. So the histogram of the canary shows that, now it's because the data is quite boring, you don't see a lot of difference between it. What you end up looking at is that, the canary seems to kind of move quite nicely. You see a large concentration on the 0 because, as we saw, this is a good thing. Why? Because the floor is not moving. Not only that, because the majority of the data set is actually 0. The number is 0. We're very close to 0. This is a great thing. So if you see the reference or the canary being much lower there, then you start seeing, well, there's something because my floor is moving, which should have shown earlier, but we didn't because the data is very similar in that aspect. What you see, though, is that the canary is looking quite nicely where as the error rates increase, you see less and less samples, less and less occurrences of the higher error, higher rate, which is great. What you see a difference between that and the reference is that the reference seems to be a little bit of clustering here, where you see the next 2 bins kind of getting together and being about the same. So the data is not as evenly distributed, and there are more samples at the higher end, definitely more samples at the higher end for the reference than the canary. So this canary is looking really awesome right now. So moving on to the next part, which is this basic, simple test of a null hypothesis, and I kind of highlighted what is very important from this test, which is it's like in justice, in criminal justice or anything else, you're always assumed to be innocent than to be guilty, and until proven otherwise. So it's the same thing for a null hypothesis, which means like the new build is assumed to be innocent. What does that mean? is that the new build is assumed to not be introducing any problems on its own until proven otherwise. So you're going to run, now we're going to the next step here, which is run some more statistical tests that will basically validate or nullify or invalidate the null hypothesis. So it's basically the new build is as good as the old build, and it's assumed to be free of errors. All right, so basically, the first test that we're going to cover is ANOVA, which is a very basic analysis of variation. And what it's validating is that the builds are the same as far as variation goes. The analysis of variation. So it's basically, and the next thing is, what is a p-value? A p-value is another very important part of concept of statistics, which is, it basically means that if you have a p-value tells you what your confidence interval is, and we usually aim for 95%. What does it mean then? If you get an observed point that is outside of the confidence interval, that means that the null hypothesis is going to be rejected. So just keep that in mind. If you have for using a p-value of 95% confidence interval, that means we want a p-value of 0.05, which is 5%. Right, so anything that is more than 5% means that we're outside of that confidence interval, therefore we reject that hypothesis. So the key number here is the 0.05 to keep in mind. All right, so, and there's another very important piece of data for analysis of variation, which is the Fstep, which means that it is explained variance over unexplained variance. So it's basically, if you end up with a very small number, there's a lot of unexplained variance. If you end up with a, with a very large number, there's a lot of very explained variance. So finally, jumping into the result set for this ANOVA test run on the two data set, we end up with a p-value of 0.0143. As if you recall me saying earlier that we wanted something that is less than 0.05, so that this means that the null hypothesis is not rejected. That means that we have confidence in our Fstep. And our Fstep being 6.03, that means that we have a lot of explained variance. That's a great thing, right? So it's basically, what it's basically saying is that the builds are similar, and therefore it's not seeing enough difference in the variation of the data to reject them as different. All right, and then the next and final test, which is a Welch t-test, which uses a very similar concept, but then it makes analysis of the means, which means that the Welch t-test will reject or corroborate the null hypothesis based on the variance of that mean. So this is the final tiebreaker that I always use, because it means that if the means are proportionally different and rejected by the test, it means that the builds are definitely different. And so when we get here there's much more jumble, but again, we're looking at the data, which is very important, which is the p-value against 0.14, which is very similar to the ANOVA test, which is less than 0.05. That means that means that our t-statistic is meaningful, and we have a number that is close to 2. So the t-statistic, which was in the previous slide, that kind of explains a little bit, what it is, the math behind it, but what it means that we want the t-stat to be as close as possible to 0. So what I've seen in my experience so far is that when we see something, even though we end up with a meaningful p-value, we may end up with a t-stat that is very high and that just gives us less confidence in the build. All right, so basically what this all means is that the data in the dark canary actually looks very good compared to the canary, and therefore we have all the data we need to go sign off and say, yes, we can go to production. So why do this? First of all, eliminate speculation. We used to end up, putting these graphs and people would start pointing fingers saying, oh, this might be because of that, well, look at this, you look at a longer period of time. So this removed all the guesswork, which is the second point. Eliminate subjective interpretation. Again, people pointing a point to the graph and look at this, look at that, I think this is okay. That was just gone. Standardized on quantitative methods, which means like this is easy to automate and but it's quantitative. And then you build your margins, or you fail your test, you see too much variance, you go ahead and reject the build. And that's as simple as that. So you build confidence in your process, earn confidence in your process, and build data for future comparison. Now we've been doing this for several months, for almost a year now, so basically we have a whole trove of data we can go back and refer to when we said it was okay to ship and it wasn't okay to ship, and when we said it wasn't okay to ship but it was okay to ship. So basically it's something that we keep adjusting. This basically has solved most of my problems when we were deploying builds, because it eliminated a lot of the guesswork and a lot of the arguing back and forth, should we deploy this or not, there's an important fix. It's like, so this gave us all the tools and all the confidence we needed to stand up and say, basically, this new build is not right, we can't accept it, it includes high risk to production. And then so that we could focus our time on much better things than basically always debugging production problems and always, not being able to sleep at night, wondering what you shipped that you shouldn't have shipped. So this has been a very powerful tool set that I wanted to share with this audience. And that's it. I'm open to questions now, but I'll ask the first question, which is basically how much data to use, which was, I didn't want to end up with too many slides. So it's basically like how much data to use. So basically, we found that if we use too much data, that we end up with very low p-values and very high t-stats, or everything's out of whack. So it's basically, I covered that in the paper. You can download that, read that. But what we found is that 180 samples seems to be the right thing, and basically we're pulling samples from the most busiest periods of traffic, which means like the problems are more likely to occur. Because if you're pulling data from the middle of the night when you have just a onesie-twosie using the website, somebody who's just having insomnia and shopping too much, it doesn't really help a lot because there's very little capacity that is being used in the system, so everything seems to go fine. Problems start occurring when we have a larger set of traffic, and then resources start getting the dispute, the challenge, and the wait times for other resources and other auxiliary services start going up, and that is when problems tend to occur. So right now we're settling on about 3 hours of data, 3 to 6 hours of data with samples about every 2 to 5 minutes. Seems to be like the sweet spot for when we can capture the most likelihood of errors and have data basically be able to run the statistical test that will correctly accept or reject according to the hypothesis that was developed. Yes, sir, in that first question. That is a great question. So repeating the question is that how do you make sure that that you're eliminating false positives and false negatives too? It goes both ways, because the data set could be obscuring problems. So in this particular case, I shared error graphs, 400 and 500s. If I'm returning 200s, but the data that I'm returning is bad, this test is not going to cover that. So so the answer to that is that you run the statistical test for every metric that you judge important. If anybody here works on aligned systems, you probably know that you're probably tracking hundreds, if not thousands, of metrics. So it's basically things start getting out of hand, because if you're running this test on thousands of metrics and hundreds of metrics, then you may end up rejecting and accepting things for the same build, and then how do you make a decision? So what we did was we focused on the most important metrics, and in your particular case, their particular question is that we have other metrics that track whether data came from fallback, whether data came from whether I returned 0 deals, which is basically I returned a 200, but I returned an empty response, which is a valid scenario. But if I see that number varying between the builds, it's a more likelihood that I'm basically timing out and returning nothing, rather than the client asking for that data, asking just for the what I call the auxiliary data in that response, rather than the deal set itself. So it's about tracking the handful of very important metrics that give you the most indicative answer about whether things are moving or not. So we have to settle on about 10 to 15 metrics across our systems. We have multi-tier systems. So it's basically, and the collection of all the data is what lets us make that decision, but not just on one simple metric, which is the case here, which I've shown here, which is just one metric. This needs to be brought to at least, I would recommend a minimum of 5 metrics. So you have your error rates, you should apply that to latencies, and you should apply to other, like quality, response quality metrics, such as the deal distribution in our case, 0 deals. We have different distributions. Everybody here, I hope you use Groupon, so you know we do local deals, we do goods, we do travel deals, so we have certain guidelines on how much we should have of each, and if we're doing too many local goods or not enough, or too many travel deals, there's something wrong happening in that process. So, so anyway, so the aggregation of the results and all those metrics is what gives us the final go, no-go for the build. Thanks for the question. Yes, sir, in the back. Next. Yeah. Yeah. So what we do usually is so the first stage of the investigation of what we do here is basically to compare the data and just basically know that we do have a problem. So when we reject the build, then basically the next stage of the investigation is finding out what is causing this, and then the severity comes out of that. But it's just that, unfortunately, I couldn't share more interesting data here. Sometimes I like to see when I go back to a box plot that you end up. The histogram would be a good one, but sometimes I end up with the box plot, which one box is way up here, the other box is way down there. Right? It's basically, and then when you look at it, it's like, well, something is terribly wrong. So we don't even need to continue with the other tests. We run them just because they're automation. I get the results anyway, but when I look at the box plot data, it already tells me that. So then after that, then you need to figure out what is changing and what's causing the difference, and then the severity comes out of that. But I rarely ever find that anything that moves the box plot significantly, moves the data significantly to cause us to reject it, is okay to ship. I haven't seen that yet in almost a year of doing it. So this seems to be like whereas, another thing that I wanted to share here, but I was prevented from doing, which was we track our pass rates, execution and pass rates of our functional tests over time, and there's great variance in that. And, hardly ever hits 100%. Even, first of all, because we have over 1,000 test cases, is basically the likelihood of something timing out and not working 100% is extremely high just because you have so many of those. But then the other thing is that investigation is very simple, because when you fail a particular test, you look at that failure and that severity is already built into the test case because it's a customer scenario, it's something that's already in there. But if that data is looking great, because we don't go to the step until that data is looking great, and then because we do that in the pre-staging environments, when we go to production, that means we already signed off on it and all the functional scenarios are checked. So that usually means that something bad's lurking underneath, and therefore we should reject that build and do the investigation, and then find, well, we missed this particular test case, so we go ahead and add the new test case to the data set so that we can prevent that from happening again. So it also teaches you what you're missing in your coverage that allows you to create new test cases. All right, next question. Yes. Yeah, so that is just a common, statistical method. You can use whatever null hypothesis you want. So if you look in the results, the alternative hypothesis, true difference in means is not equal to 0, so you can test against that. Fortunately, we're not doing any life critical systems, so it's basically we try to go with the more optimistic null hypothesis, which is you're assumed innocent and still proven guilty. And understand that when we got to that point, we already ran all of our functional validation, and we see no difference between that build and the next one, so we have no reason to really believe otherwise. But yeah, for more life, I do not have any experience doing that myself, but I would say that for more life critical systems, avionics, and those types of things, then the testing and the hypothesis has to be a lot stricter. Next question.
Where in your process does this fit in?
Yeah.
Where at the beginning you stand up production, traffic feels like it's lots of responsibility and yourself, and that's what you're doing.
Right.
Is this like whatever level of that's good, right? It doesn't know what they're doing. Okay, we're all good with this, we're gonna look at we're gonna build it on, okay, now what do we do? Staging environment, we have to do gathering data.
This is actual production. So when we got to this is the very last stage before we go to production. So we've been using Canary systems for a long time, even before I joined that team. But people were just staring at graphs before, so it was already part of the release process. And we're finding ourselves copying and pasting graph data, put into a document to back up our decision to ship or don't ship. My motivation to build this was because I wanted to add some quantitative data that backed up my decision, not just based on visual inspection of the graph, but actual quantitative data that would back up my decision that this data is not significantly different, or if it is, that this data is significantly better than the other one, or worse. Because it's possible for you to have a rejected null hypothesis because the means are so different, but if the Canary mean is so much lower than the reference build, that means the Canary is much better built, so we should definitely go with it. Or it could go the other way around, where the mean of the Canary is so much different, so much higher. Or for an error rate, that's something that is bad, so we already know that we can't go with that. So this was put in place to prevent us from shipping anything that we hadn't already been able to catch before going to production. Yes, sir? Any questions? Absolutely. At this point in time, I've had no data to indicate I shouldn't trust this process. I've never made the wrong call, and I'd say me is not me because it's just the data speaking for itself. So what I wanted to do with this, my goal here was to eliminate subjectiveness and speculation from the process, and they completely eliminated that. So it's basically, I have all the data that I need to make a confident decision of ship, no ship, based on that. And I have the data to go back and push back. So yes, absolutely. So I cannot speak to, I'd love to be able to disclose more data, but I cannot, unfortunately. But this is definitely getting built into next iteration because my role is, I run a team called operations and quality, so I do DevOps, operations, and a bunch of other things. So it's like, and we do our deployments and monitor the systems and do troubleshooting on the systems. So it's basically, next stage for us should be able to ship a lot faster. That was another motivation for this. You should be able to, how do I get enough data in the minimum amount of time, which is 3 to 6 hours, for me to make a confident decision for me to go to production or not. And this has been the answer for me, for us at least. I had another question over there, yes? Yeah, so just drawing a parallel to Penny's presentation earlier today, if you guys watched it, it's kind of, I needed to do something different, and I needed to go bold, because the system that was not working out for me. I was wasting cycle after cycle, and they say, oh, you try to make this as a joint, we all own this together. It doesn't happen that way. You put a build in production, it's bad, the finger points at you. You know, it's just like, even though you didn't write that bug, it's just as simple, because your job is to prevent that bug from going to production, whether you know it. So this is, you're literally looking for a needle in a haystack. This is like a magnet. You put the magnet in the haystack and the needles just pop up and stick to the magnet. I think it's the best analogy that I can come up for this. Because you're no longer looking for it. The needles come to you. And then you show them, here are the needles. I don't know what they mean exactly, but I know it can't go to production like this. Does that make sense? Oh, I started, first of all, I was doing this by hand using R. And after, it was very rough in the beginning because people just weren't used to it. And you just start throwing this data and they start, what is this? You know, it's like, what are you talking about? I've never seen this. But then when you start talking about null hypothesis, p-values, and things like that, people are like, well, first of all, it goes over their head. It's very unlikely that you have somebody who knows enough about statistics, but you're like, hey, you explain the concept and you basically explain to them why you're doing this and what this actually means. And they're smart, they understand. So it's basically, the pushback stops immediately. But I took about, say, 2 to 3 months to really build the confidence. Then I automated this using Python and other libraries, SciPy, Pandas, NumPy. Between the 3 libraries with Python, you can do everything that's here and automate everything. So it's very easy to read. Yes, sir, in the back. That's a great question. How many deployments production? When we first started doing this, we were rejecting 1 build every other week. And about doing, I can't disclose how many deployments we do, but basically I'd say it's a significant amount of rejection rate. The beauty about this process is that it kind of fed on itself and it just raised the quality bar. So now we rarely ever reject a build because the data is just, I believe that because we've been able to reject, confidently reject and be right about rejecting the build, that is just the quality was pushed upstream because people didn't want to be put on the spot because they're the ones that caused the issues that stopped the build to production. Because I worked in a system that's called relevance. Basically, every time any of you go to Groupon, it's going to figure out who you are, where you are, and give you that deal set that we think is more likely, that you're more likely to buy. So it's basically, we have tremendous financial impact in the company. So any changes we make, anything that impacts the quality of that system is financially impactful to the company in a negative manner. So this system has allowed us to reject more builds, which has brought more sense of ownership and, just basically simple quality awareness about code changes. There are a few other things that we have done as well. I won't go specific into that to push quality upstream as well, which was part. So I can't credit just this for that, but it's definitely part of it. Yeah. Yeah, pretty much every time that we reject the build and we do the investigation and find what we didn't find, that ends up with a ticket for somebody to create a test case. I'm still working on trying to get my developers to write those test cases. They usually tend to sit around for a while, and then we just kind of go, hey, I'll catch this again, so I'm not worried anymore when I'm not going to be able to catch it. But the problem is we shouldn't be reintroducing the problem, right? So So I'm still working on that, but at least, for things that are more important and more critical, then we definitely create the test cases immediately to prevent them from happening again and be able to catch them upstream because of other. What we've done is that we push the quality upstream so that every commit goes through a series of gates, quality gates, before it can even be allowed to emerge into master, so that there's no PR ever going to introduce, a new error that we already know of. So by the time a PR has been merged, it's already been, everything's been green, including from a performance perspective. Yes, sir. Yeah, so not a significant amount. So we were already using Canary, so we already had and we were just basically, because our system's been online for several years, so we have a multitude of hardware. Some of it, Groupon actually comes with some data centers, and we have older hardware and we have newer hardware. So basically we start pushing this to the older and older hardware. Why? Because it's more likely to fail. The one that is more likely to expose those because it just runs slower, so it's more sensitive to latency, it's more sensitive to contention and other things like that. And also because it's older, it's lower, it processes a much lower amount of production traffic. So this is basically, we just have, we already had our VM, set of VMs with our quality apps running on them. It's just added another cron job on it that just runs this regularly posted to a database, and then we look at it on a dashboard. And it's pretty straightforward. It's not a significant add in terms of resources. Welcome.